Summary of curve sketching. Now here we're sketching curves. That means that the graphs that you're drawing do not have to be exact. They're just sketches. And here we're looking at a bunch of different tools that you can use in order to sketch a curve. You have domain, intercepts, finding symmetry of a graph, finding the asymptotes, finding local maximum and minimum values, finding out where the graph is increasing or decreasing, and finding out the graph's concavity. These three right here are calculus tools. You didn't know these until now. All of these ones are tools that you should have seen and used before in order to graph sketches of curves. So I'm going to spend most of my time talking about these, and then I'll kind of just quickly review the other tools that you can use in order to draw a rough sketch of a graph. So I'm going to graph number 3. Now in order to graph number 3, I'm going to start with finding the critical points on this graph. So I'm going to need, in order to do that, I'm going to need y prime. So I take the derivative of the function, and then I set it equal to 0. I set the derivative equal to 0. After I set the derivative equal to 0, then I solve. The first thing I did is I divided everything by -3 so that it looks like a more simple problem to factor. And after I do that, I get x minus 1 times x minus 5. So my two critical values are 1 and 5. Now 1 and 5 are your x numbers right here, 1 and 5. What I'm going to do now is I'm going to draw that it's commonly called a sine line graph. This is actually just the x-axis. So this line represents this over here, but it's kind of like notes or something, one way that you can show your work. So I'm going to draw these dotted lines right here at my critical values, where the critical values are. And these numbers that I picked are just numbers that are in those intervals. Like 0 is on the left side of 1, and 2 is between 1 and 5, and 6 is after 5. So technically, I mean, I could have picked 3 instead of 2. I could have picked 10 instead of 6, but it doesn't matter which one you pick, just as long as it's in that interval. When I plug in 0, that one's pretty simple. I find out that my result is going to be negative. I get a negative 15. That's all you need from that. Now let's find the sign of the next interval. So when I plug in 2, let's see, I get negative 12 plus 36 minus 15, and that's going to end up being negative 27 plus 36. So that means I'm going to get a positive number in between the 1 and the 5. Then let's try the 6. We plug in the 6. We get a negative 3 times 36, and then 18 times 6 minus 15. Negative 108 and positive 108 minus 15. It looks like I get a negative there as well. And so what do these signs tell us? The negative, the positive, negative, they tell us that the graph over here that we're trying to graph is decreasing before the x value of 1, increasing between the 1 and the 5, and then decreasing after the 5. Now normally when I'm graphing this, I like to do this for new sketchers. I like to draw my critical value lines here, and I like to write this out. Now I'm just being very detailed to help you guys catch on to this. So the graph is decreasing, increasing, and then decreasing. Now, using the first derivative to find where the graph is decreasing and increasing is commonly called as the first derivative test. Remember, we find critical points by setting f prime equal to 0, or finding out where the derivative is undefined. That is the first derivative test. And so the next thing I want to do is I want to find out where this graph is concaving up and concaving down. So in order to do that, I need to take the second derivative. And so after I take the second derivative, I set that equal to 0. And what this is going to do is it's going to help us find the inflection point. The inflection point for this graph is x equals 3. So I draw my x-axis, except this time it's kind of like the same thing we did here, but this time I'm not finding where the graph is increasing and decreasing. I'm going to find out where the graph is concaving up and concaving down. So I put a 3 right there. I got my 2 tester points. I picked 0 and 4. Again, you can pick any tester points you want. After I plug in 0, I get positive. When I plug in a 4, I end up getting a negative number. So you get negative 24 and 18, which will give me negative. So this interval right here will all be concave up, and this interval over here will all be concave down. Now, one thing I want to make sure you guys take notice of is the concave up, how the graph would be decreasing and increasing. Just because it's concave up doesn't mean it's increasing. It means that the slope is slowly increasing. So even though the graph is going down right here, soon the graph will be increasing. And during this whole time, it's concave up. The graph, which is what we're trying to graph, is concave up. Same with when it's concave down. When the function, this guy up here, is concave down, it means that it's increasing and decreasing. Okay, it's like it's going, the graph will be increasing and decreasing, and the slope is slowly decreasing. So I'm going to draw an inflection line right there. This is commonly called the second derivative test, and that's where f double prime equals 0. So in order to sketch, we need a point. We need to find a point somewhere on this graph so we can just do our rough sketch. There's many different ways to find points. There's a few important points that one should find, like Y-intercept. This one is a give me. If you can find a Y-intercept point and that helps you graph, then I suggest doing it. You set x equal to 0, and in this case, when we do that, when we set x equal to 0, we get 2. The other one are the x-intercepts, and you guys are most familiar with this because you did a lot in Algebra 1. That's when you set y equal to 0, and then you solve it. Now this graph, actually, when you try to solve it, when you try to solve for x when it equals 0, when the function equals 0, it doesn't come out with pretty x-intercepts. So x-intercept points actually don't help us for this graph. We're not going to use that tool. The other thing we could do is we could find the max and mins, and that's when we take the critical points that we found over here, the 1 and the 5, and we plug them back into the function up here to see if we get some clean numbers, and we can find out the max and min points. So I go ahead and I do that. I plug in the 1, and let's see, I get negative 5, and so I put negative 5 right there on the negative 1 critical point, and then I plug in the 5. Let's see what I get on this one. I think it's 27. Yep, 27. Okay, and then I put my point right there. Now I have points. It makes the graph easier to sketch, and so I just ended up starting right there and sketching. Notice that in this interval I'm decreasing. The graph is decreasing. Then as soon as I enter this interval, I'm increasing, and then I'm decreasing again. This purple line just tells me where the inflection point is. That's actually another point we can find. We could plug in 3 since that's an inflection point, and then we can find out where the line should actually start changing its concavity. Let me go ahead and finish it right there. That's a quick sketch of the graph. Now, really quickly, let me remind you guys about these tools. You have domain. Remember, domain is wherever those are the x values that you're allowed to plug into the function. Most of the time you look for where the function is undefined so that you can define its domain. I honestly don't use this that much when I curve sketch. The next is intercepts. Intercepts are usually really simple to use, and I just showed you that. The y-intercept you should always use because it's way too easy to find. The x-intercept most of the time is not going to work for you because I want you to practice calculus, the calculus tools. And since you guys are pretty familiar with finding x-intercepts, a lot of times that doesn't work. Symmetry. Symmetry, let's see, there's 2 different forms of symmetry. There's when the function is even, and what you do is you plug in a negative x into the function and see if you end up with the same function. If you end up with the same function, that function is even. Now why does that help? Well, let's take x squared for example. Here's x squared. If I chose this x and I chose this x over here, so like this would be 5, this would be negative 5, they both get the same y value. So really, if you just graph this side, then you just copy it for the other side. And so knowing that the graph has symmetry about the y-axis, if it's an even function, it makes the graph easier to graph. An odd function, think of like x to the third or x to the seventh. Your graph goes like this. And if you were to choose negative x and x, or negative 5 and positive 5, you get negative y for the negative x, and for the positive x you would get a positive y. So the y's are actually the same, except one's positive, one's negative. And this one also has symmetry about the origin. So if you had this side, you just need to copy that side, but with the opposite y values. Like if this y value was a negative 3, then this y value up here would be a positive 3. So that's symmetry. And then finally you have asymptotes. You have vertical asymptotes and horizontal asymptotes. I use the limit here to define the horizontal asymptote, but for horizontal asymptotes, that's when you look at the degrees. Like let's say the degree is greater on the bottom. If the degree is greater on the bottom, then you know that the horizontal asymptote is y equals 0. But if the degree is greater on the top, this is not a horizontal asymptote. So no horizontal asymptote for that one. Now if the degree is equal to the top and the bottom, then what you do is you take the coefficients that are in front of the highest degrees, and I just made up 5 and 3, and then that would be your horizontal asymptote. You just divide those. And don't forget, a vertical asymptote is when the denominator equals 0, so you just set the denominator equal to 0, and that gives you your vertical asymptotes.